Good morning, my name is Cesar Yok. I am the founder of the Bronze Institute for Urban Systems. Today is April 24, 2020, and I'm going to go over one of the elements of systems planning, the second element of systems planning. The element 2, which is systems planning, follows the laws of thermodynamics, especially the second law, entropy. Archetype: how long does a building take to fall apart without the addition of energy? What is the energy potential of space? Table of contents. First is a glossary. 2. Laws of thermodynamics. 3. Geological, ecological, time and our consumption. 4. Entropy. 5. Population. 6. Energy consumption. 7. Ecological footprint and biocapacity. 8. Fragmentation. 9. Energy consumptive norms and ideas, vertical gardens. 10. EVOI. 11. Learning from nature, ecomimicry. 12. Thermodynamic architecture. 13. Maximum power. 14. Let nature provide and don't destroy ecosystem services. Glossary. Thermodynamics is a branch of physics that deals with heat and temperature and their relation to energy, work, radiation, and properties of matter. Energetics, the branch of science dealing with the properties of energy, in which it is redistributed in physical, chemical, or biological processes. Carbon footprint, the amount of carbon dioxide and other carbon compounds emitted due to the consumption of fossil fuels by a particular person, group, etc. Glossary. Thermodynamic architecture. Architecture designed based on the laws of thermodynamics. Carrying capacity. The number of people, other living organisms, or crops that a region can support without environmental degradation. Ecological footprint. The impact of a person or community on the environment expressed as the amount of land required to sustain the use of natural resources. Glossary. Ecological footprint. The ecological footprint measures human demand on nature. The quantity, for example, the quantity of nature it takes to support people or an economy. It tracks this demand through an ecological accounting system. So to your right, you have a picture of an analogy of the ecological footprint. This is the where humans demand for nature, or what it takes to support a system. Glossary. On the demand side, the ecological footprint measures any individual or a population's demand for plant-based food and fiber products, livestock and fish products, timber and other forest products, space for urban infrastructure, and forests to absorb its carbon dioxide emissions from fossil fuels. On the supply side, a city, state, or nation's biocapacity represents its biological productive land and sea area, including forest lands, grazing lands, croplands, fishing grounds, and built-up land. Power in physics. Description. In physics, power is the rate of doing work or of transferring heat. For example, the amount of energy transferred or converted per unit time. In the International System unit, the unit of power is the watt, equal to 1 joule per second. Energy. In physics, the capacity for doing work. It may exist in potential, kinetic, thermal, electrical, chemical, nuclear, or other various forms. There are, moreover, heat and work, for example, energy in the process of transfer from one body to another. Glossary. Specifically, energy is defined as the ability to do work, which for biology purposes can be thought of as the ability to cause some kinds of change. Energy can take many different forms. For instance, we are all familiar with light, heat, and electrical energy. Glossary. Ecological deficit or reserve. An ecological deficit occurs when the ecological footprint of a population exceeds the biocapacity of the area available to that population. A national ecological deficit means that the nation is importing biocapacity through trade, liquidating national ecological assets, or emitting carbon dioxide waste into the atmosphere. An ecological reserve exists when the biocapacity of a region exceeds its population ecological footprint. Nature reserves. Description. Ecosystem services are the many and varied benefits to humans gifted by the natural environment and form healthy ecosystems. Such ecosystems include, for example, agro-ecosystems, forest ecosystems, grassland ecosystems, and aquatic ecosystems. Evolution. Evolution is a change in the heritable characteristics of biological populations over successive generations. These characteristics are the expression of genes that pass on from parent to offspring during reproduction. Right now, I am going to go over the laws of thermodynamics from a physics point of view. The zero law states that if two bodies are in thermal equilibrium with some third body, then they are also in equilibrium with each other. This establishes temperature as a fundamental and measurable property of matter. The first law states that the total increase in the energy of a system is equal to the increase in thermal energy for the work done on the system. This states that heat is a form of energy and is therefore subject to the principles of conservation. Thermodynamic equilibrium, zero law. Object 2, Object 3, Object number 1, which is a thermometer. When two objects are separately in thermodynamic equilibrium with a third object, they are in equilibrium with each other. So let's say Object 2 has a temperature of 70 degrees and Object 3 has a temperature of 70 degrees. That means Object 1 will also have a temperature of 70 degrees according to this law. Examples for first law of thermodynamics. The increase in the energy of potato in an oven is equal to the amount of heat transferred to it. In the absence of any work interactions, the energy change of a system is equal to the heat transfer. So what does this mean? It means that energy is never lost. So the energy is never gained or lost. The quantity always stays the same. Laws of thermodynamics. The second law states that heat energy cannot be transferred from a body at a lower temperature to a body at a higher temperature without the addition of energy. This is why it costs money to run an air conditioner, entropy or disorder. The third law states that the entropy of a pure crystal at absolute zero is zero. As explained above, entropy is sometimes called waste energy. For example, energy that is unable to do work, and since there is no heat energy whatsoever in absolute zero, there can be no waste energy. Entropy is a measure of disorder in the system, and while a perfect crystal is by definition perfectly in order, any positive value or temperature means there's motion within the crystal which causes disorder. For this reason, there can be no physical system with lower entropy, so entropy always has a positive value. This is the second law of thermodynamics. So it always goes from hot to cold, heat transfer. So second law of thermodynamics has to do with disorder. Everything leads towards disorder. It takes energy, to decrease the disorder, which means lower entropy. So with higher entropy, that means it's always disorder. So you already have two pictures. You have an industrial site, and the bottom picture is somebody mowing a lawn. These two systems lead to more disorder. In the industrial site, it's always have waste, so it's always leading to disorder. The energy system is always leads to disorder. One fact about the laws of thermodynamics, or the second law of thermodynamics, is everything leads to disorder, and most of the time it's waste. The other fact about the second law of thermodynamics is that in the first law it has to do with quantity. The same amount is always the same. So in the 30 or something of matter, it's always going to be 30 something of matter. The second law, there is an issue of quality. So when you go to a process, there are processes in which you have more useful quality and less useful quality. So it's usually for more useful quality of energy to less useful. So at some point the energy is not useful anymore. That would be the second law of thermodynamics. Then here you have more energy being used in the system at a faster rate. In those two pictures, that's what it shows. Geological, ecological time, and our consumption, time of human consumption. Human time and natural resource use. So make believe this is the time that we use natural resources and we use energy. So we use energy at a faster rate compared to minerals and fossil fuels take millions of years to make. They're finite and produce a lot of waste. This has to do with the second law of thermodynamics. Like I said, everything leads out to total disorder. So when you go to a different process, one process to a second process, you always have waste or heat loss. In this case, it has to do with disorder. That means when you go from more energy, it always leads to a disorder, and the way that disorder is shown in a system is through waste. Time it takes for nature to recover is greater than how fast we extract. Laws of thermodynamics, less useful energy. So you go from useful energy, but when you use it, you go to less useful energy. So at a certain point, you can't use that energy anymore. It's not useful for any type of work. Now you have ecosystem services. This is the rate of ecosystem services. Let's say you have a forest, and then it takes 50 to 100 years in order for that forest to mature. And then that provides services to nature and us. Like you know about trees, trees provide oxygen to photosynthesis, and it also has other services. Time it takes for nature to recover is greater than how fast we extract. Laws of thermodynamics, less useful energy. Again, in here we are extracting at a faster rate than which ecosystems could recover. So we need to be able to have a balance between those ecosystem services and how fast we extract. We have to be able to let nature recover itself, but we are extracting at a faster rate. It's hard for nature to recover itself. Entropy, everything leads to disorder. In cities, you always have energy being used to repair buildings or to construct new buildings and to construct roads. Cars also need to be repaired. Homes always need to be repaired, and human beings also use energy in order to be able to repair cells. So everything in life requires energy in order to reduce disorder. So in this case, you have a picture of some folks working in a building, and then that building is leading towards disorder. Building entropy. Here, every building always leads toward disorder. So it takes energy in order to maintain that order. But over time, that energy is less useful. So at some point, it degrades to a point that it doesn't matter how much energy you put there, that it won't be useful anymore. Because the energy goes from high energy usefulness to low energy and then nothing at all. This is entropy again. Waste. Waste is how entropy is shown in a city and a natural system as well. In here you have all these pictures of garbage, of things that used to be useful but they're not useful anymore, so they are thrown away. So we are using new minerals in order to create a new technology, and then the old technology is just left in a landfill, and then it takes a long time to degrade. Now we're going to talk about population. So we're going to go into more broader and a global scale. The size of the world population over the last 12,000 years. In 2019, there were 7.7 billion people. In 1700, there was 600 million people. In 1900, there was 1.65 billion people. And now in 2019, there are 7.7 billion people in the world. Population density. Population density is defined as the number of people divided by land area, measured in square kilometers. Kilometers to the second power. As you notice here, the places that have the most population density are India, the West Asian, European countries, and Central American countries have higher density. This is a 2013 map of energy consumption per capita. As you notice, the United States, China, and some European countries have high energy consumption per capita. So most developed countries use a lot of energy. And this affects the ecological footprint. Again, you can see here the darker areas in the United States, India, and other European countries and Asian countries have high ecological footprint. That means they use a lot of energy. The countries ranked by total ecological footprint in global hectares. China is number 1, United States, India, Russian Federation, Brazil, Japan, Indonesia, Germany, Mexico. They have high ecological footprints. Deficit, footprint, and biocapacity. Again, you can see the United States is in the red, Mexico is in the red, European countries are in the red, India and Asian areas are also in the red. What does that mean? An ecological deficit occurs when the ecological footprint of a population exceeds the biocapacity of the area available to that population. A national ecological deficit means that the nation is importing biocapacity to trade, liquidating natural ecological assets, or emitting carbon dioxide wastes into the atmosphere. An ecological reserve exists when the biocapacity of a region exceeds its population ecological footprint. Again, so these countries have high ecological footprints, but their biocapacity is lower than their ecological footprints. So there's a deficit. They're consuming more energy than what is available or what nature could provide. Most tend to be developed countries. Fragmentation decreases the ability for an ecosystem to sustain itself. Now I'm going to go over some of the issues and some of the problems that cause because of the high ecological footprint and the natural resource use. So this is about fragmentation. Destruction and degradation of natural ecosystems are the primary cause of declines in global biodiversity. Habitat destruction typically leads to fragmentation, the division of habitat into smaller and more isolated fragments separated by a matrix of human transformed land cover. This is a picture of fragmentation. In parts of Ontario's southern border forest, companies have experimented in logging in a variety of special configurations to avoid clear cuts. The forest hosts a wide variety of birds and their insect prey is threatened by fragmentation. The fragmentations affects ecosystems. It affects their adaptability and resiliency. When you have fragmented ecosystems, it's hard for that system to be resilient. It takes many years for that system to be able to be resilient. So every species of animal and plants and trees, and they are working together in a system in order to be resilient. In fragmented area, the ecosystems are destroyed. They're not resilient anymore. It takes a long time in order for the system to be able to be adaptable, resilient, and the fragmentation kills that resiliency. This is a Google map of my neighborhood. It's fragmented. This is New York City, and right now is a section of the Bronx. So this system requires a lot of energy because nature cannot be able to sustain itself in here. It requires input from human. It requires fossil fuels. It requires a lot of energy in order to maintain the system because it's fragmented. Because of the fragmented landscape, it takes an immense amount of energy to maintain this type of grid. These studies of landscape shapes to determine which landscape has the most energy potential. Here you have different type of shapes. So these shapes determine how much energy potential these areas have. The grid has some limitations as to how much energy potential it has. These studies of landscape shapes to determine which landscape has the most energy potential. So these are different shapes of landscapes. And then this is the sun rays hitting the landscape. And then through studies you need to determine which landscape has the most energy storage and most energy potential. The grid has some limitations. It has much energy it's able to get locally. This is a Brooklyn Bridge Park, lawn mowing. Energy is needed to maintain the system. You require fossil fuels and fertilizer to maintain the system. Lawn mowing is not natural and it is not sustainable. Most people are talking about vertical gardens as a way to go, to have more food and have a new type of agriculture. Vertical farming requires immense amount of energy to maintain. It doesn't follow natural ecosystems. Humans have to input energy to keep this up. It is usually fossil fuels that maintain these systems. So this here takes a lot of energy and it's not natural, meaning you don't have evolution, natural selection, ecological processes, ecological systems that are maintaining this. This is maintained by energy input from humans. Most likely it's fossil fuels. Requires human energy to maintain the system. Since it is fragmented, the system cannot sustain itself. We need to know the lowest amount of space needed for a system to sustain itself. And this system right here, This is a great infrastructure. Uh, in here, you require a lot of maintenance. That means humans have to maintain the systems unless there's enough species of flora and fauna in order for it to sustain itself. But usually in these cases, there's not enough space and there's not a lot of diversity in flora and fauna. Flora means trees and plants and flowers. Fauna means animals or organisms or microorganisms. They work together in order to maintain the systems. So since this is a fragmented space, it's hard for that system to sustain itself unless humans maintain them. Energy. Evolution of power outputs of machines available to humans. At first, a man pushing a lever, they could get 40 joules per second. In 1940s, he had steam turbine, and the output was 165 million joules per second. Nuclear power plants in 1970 gave about 840 million joules per second of output power. This is a graph showing that fossil fuels have key. In a certain point, it doesn't matter how much energy you use in order to extract fossil fuels. You're going to have a limited amount of fossil fuels that could be extracted. This is the graph of world production of coal, oil, gas with forecast. No demand constraints for an ultimate and population for UN 2003 forecast low to medium. You have here population. It peaks at a certain point. Coal peaks at a certain point. Gas peaks at a certain point. Oil peaks at a certain point. At a certain year, it peaks and then you get less in return. It doesn't matter how much money you put in, how much energy you put in, you get less in return. Energy return on investment. This is a ratio. Energy return for the energy gathering activity divided by energy used to get that energy. So this is a quantity. It has nothing to do with the energy that is being inputted. So the energy could be fossil fuels in order to get something in return. This is just a ratio of how much energy is used and how much you get in return. Equal energy return on investment. Question: where does the energy come from? Here is a graph for the mean EROI. So here you see that hydroelectric has a high EROI compared to the other ones. Coal also has a high EROI, but coal is a fossil fuel. So it also has waste. Well, everything has waste for the fossil fuels, leads to all the major problems like climate change because of the CO2 concentration and also the extraction of minerals and extraction of these resources affects and at times kills off marine ecosystems and earth ecosystems. This is the EROI or the minimum EROI. It says you have 50-to-1 ratio in order to have some form of art. For the blue line on the top, that means that's where we are right now. We are consuming at a high rate. We need to be able to move down in order for energy to be able to replenish itself. Move away from the car power down electric cars or e-bikes. This is a very energy intensive. E-bikes, like I will show before, use cobalt and other minerals in order to make them. Cars as well. Cars use rubber, they use plastic, and they use other natural resources in order to make them. And you also have the electrical system that's connected to it. And most of the time, in this case, you use fossil fuels in order to electrify these cars. This is the reason why It's important to move away from the car paradigm. Other areas in other countries are used in order for us to be able to have this type of materials in order to create these batteries for the cars, and also our phones and our laptops and most electronic things that we use require minerals that are extracted from the earth. And there are countries that are affected by what we decide to do. This is a graph of mine production of cobalt in DR Congo from 2018 to 2019. As you can see, in 2019, it was 100,000 production in metric tons in 2019 in the Democratic Republic of the Congo. So European countries and the USA get the results of the process. So minerals are extracted in the Democratic Republic of the Congo, in this case cobalt, is extracted from that country and then it's sent to other countries in order to be processed, and then we get the results of that process. This is U.S. energy consumption by source and sector 2018. As you can see, the transportation, industrial, and electric power sectors consume a lot of energy. They consume a lot of these fossil fuels. So in order to have a sustainable society, you need to renovate or innovate these sectors in order for them to use less energy and move away from fossil fuels. You need to be able to change those sectors. So this is one way we could reduce this sectors, is by having more people walking and using more bicycles, actually regular bicycles, more light rail, and transforming our roads into more natural roads that require less input of energy there. You also have to learn from nature, ecomimicry. In here, this is the process of growth for a forest. So one area you have no forest at all, and then over time you start getting all these trees growing, different type of trees growing, and through ecosystem processes it start working together in order to maintain that systems. Then here you have flora and fauna, and at a certain point they work together in order to create a resilient forest. But like I said before, if you fragment these areas, it's not able to sustain itself. And here the forest is resilient and adapted. You don't need energy from people in order to maintain this forest. So you have to learn about this, about how this forest work. Like I said before, energy hits these areas through natural processes. They're able to use the local energy to survive. Thermodynamic architecture. So buildings have a thermodynamic component. In here we have the heat in a building. Certain areas have more heat, and then how the heat is spread throughout the building. HVAC systems waste energy and they are not thermodynamically sound. HVAC systems just blow air, and more energy is wasted to keep the rooms at a certain temperature. Here's a graph of conventional HVAC systems and thermally active surfaces. So when you blow air, the way the air spreads, it takes a long time in order to heat that area. Is not suitable. You need thermodynamically active surfaces in order to provide the right amount of temperature for the whole space and spread evenly throughout the area. Ancient Rome heating systems. In ancient Rome, there was no electricity, there was no HVAC systems, So what they did underneath the ground, they used furnaces and heated these furnaces, to heat the papers that people were standing on, and also baths and places that needed heat. So you use these furnaces, you heat the ground, and then you have a temperature. When you have the right amount of temperature in that building. That was in old architecture. Energy efficiency. Efficient energy use, sometimes simply called energy efficiency, is a goal to reduce the amount of energy required to provide products and services. For example, insulating a home allows a building to use less heating and cooling energy to achieve and retain a comfortable temperature. Energy efficiency is about quantity. Maximum power includes quality. You get less useful energy through a process. For example, you have the sun. Let's say, is 100% quality of energy. You have 100% into process 1, and then process 2, you have less useful energy. And at some point, the energy is not useful anymore to do any work. Maximum power. Locke formulated the maximum power principle. He suggested that systems prevail that develop designs that maximize the flow were useful for maintenance and growth energy, and Odom used this principle to explain much about the structure and processes of ecosystems. Boltzmann said that the struggle for existence is the struggle for free energy available for work. Here is a section of maximum power from the book Energy Return on Investment, or lecture notes. The concept of maximum power incorporates time into measures of energy transformation. It provides information about the rate at which one kind of energy is transformed to another, as well as the efficiency of that transformation. As such, it is critical to understanding the role of energy in evolution. And here it has to do with the rate of energy transfer. So in ecosystems and also animals, their biology and the way they form, they're able to maximize the local energy available. So in the forest, like I shown before, the trees might be smaller at the bottom, and then the canopy might be different than all the trees. All of this has to do with the local available energy. So the way they're structured and the way the biology is, they go more towards developing a way to maximize the local available energy. It's an analogy. It's a very abstract graph in ecosystems, and the earth is more complex than this. To make believe the sun hits the deer, the birds, and the forest. So the biology maximizes the local available energy from the sun and other systems, energy systems in the forest. The same thing can be used for cities. The way they design, you can maximize the building architecture in order to get the most local available energy. Technology requires energy and natural resources. It is not the savior. It is not growth. It is a balance with the planet. Our level that nature can recover and provide for us. Natural processes, not industrial technology, to get us to a place where we are balanced with natural processes. Let nature provide. Ecological farming is the most respectful of wildlife because it produces a lower pollution of aerosols. It produces less carbon dioxide. It prevents the greenhouse effect. It doesn't generate polluting waste. It helps make energy savings. Since in the cultivation, and then the production of product it takes. These are the different ecological cycles. To your right, you see a picture of ecological cycles. You have a carbon cycle, phosphorus cycle, nitrogen cycle, water cycle, and oxygen cycle. You have to be able to balance with all these cycles in order for nature to provide and help us. This is ecosystem services of forest. The forest provides a lot of ecosystem services. You need marshlands and wetlands in order to be able to maintain water flow. You need marshlands and you need wetlands in order to reduce the effects of storms on the system. So you need to be able to use natural processes in order to withstand the effects of future storms. So there's a need of a new philosophy of growth, of understanding of natural processes. All these lies are some of the concepts that I understand that will help you understanding entropy, and that you need to be able to balance with nature. Because if we do it ourselves, we require a lot of energy, but then that energy comes from nature. And we were able to get a lot of energy because of the Industrial Revolution and because of fossil fuels. But at some point, the fossil fuels are not useful anymore, because it would take a lot of energy and also a lot of money to extract those fossil fuels, and then it won't be useful anymore. So we need to have a new system, a new economic system, a new ecological system, a new way of designing cities in order to take into consideration the laws of thermodynamics and also ecosystem processes. So the way to go is for us to change the way we live, and also to think of how we could balance ourselves with nature. There's more to it than this. This is just element 2. Later on I will talk about all the elements, and then I will tie in all of them together to see how to work on the systems approach. Thank you, and also feel free to leave some comments. I probably left some things off here. I know it's very technical, but hopefully I was able to explain it in a way that is useful for people. Thank you.